Hey folks, this is Mr. Cross, and we're going to be talking today about the fundamental counting principle and tying it to permutations. So let's go ahead and get started. Fundamental counting principle basically says that if I've got an event or something that happens m different ways, and then another event, n, and it happens n different ways, well, if I want to know the different numbers of ways that both of those things can happen together, it would be the product of those two things. So, for example, if I had 5 different kinds of bread and 8 different kinds of meat and 6 different kinds of cheese, if I wanted to know how many different ways I can combine the bread, the meat, and the cheese, it would be 5 times 8 times 6, or 240. So that's basically the way the fundamental counting principle works. And let's look at an example problem. If I give you 5 numbers, 1, 2, 3, 4, 5, and asked you how many 3-digit numbers can be made from those 5 numbers, and then I told you that we were going to do the first part with repetition. Now, what does that mean? Repetition basically means that I can reuse numbers. So that means I can create numbers that have a 1, 1, 1 or a 1, 2, 1. I'm allowed to repeat the numbers. Okay, so if it says with repetition, that's what they mean. So anyway, basically when we're going to use the counting principle, I'm going to take a look at my 3-digit number, and I know I've got a first spot and a number of ways that can make that happen, and a second digit, and a number of ways that can make that happen, and then a third spot, number of ways that I can make that happen. So why don't you pause this and see if you can figure out how many ways I could fill in each one of those digits. Okay, so hopefully you did that, and you'll, if you've got 5 numbers and I need to fill in this first spot, well, I can put a 5 there, 5 different numbers. All right, now, how many ways can I fill in the second digit? Well, since I'm allowed to repeat all the numbers, I can go ahead and put a 5 there also, because I can have 5 different numbers go there. And then the third digit, once again, because I'm allowed to repeat the numbers, I get 5 different numbers I can put there. So if I want to find out the number of ways I can put these 3 digits together, the first and the second and the third, well, basically what I do is I multiply those, and so that's going to be 5 times 5 times 5, or 125 different numbers, or 125 different arrangements. Now, if we do that without repetition, it's going to be the same kind of thing, but let's talk about what that means. If it's without repetition, that means the numbers can't repeat. So if I use a 1 in the first slot, I can't use it again in any other slots. If I use a 2 in the first slot and a 5 in the second slot, I can't use those numbers again. It means without repetition, just like it sounds. So anyway, if I go back to the first digit and I say how many different ways can I fill that spot, it's going to be a 5. Now, pause this and then tell me what you think is the number of ways that I can fill the second slot without repetition, and then the third slot without repetition. Okay, so hopefully you did that and you found out that there are 4 different numbers that can go there. I don't know what they are, but there could be 4 of them. And then hopefully you also decided that there could be 3 different numbers in this spot. So that's going to be 5 times 4 times 3, or 60 different numbers, or 60 different arrangements. All right, good job. So let's take a look at the permutation formula and see if we can tie that to the problem we just did. First, let's look at the notation. Hopefully you're familiar with this, but this means permutation, and I've got n different objects, and I'm going to take them r at a time. And sometimes they put them on a diagonal like this, and sometimes they write them like this. But basically, all 3 of these things mean the same thing. It just means I got a permutation. The first number is the number of objects, and then I'm taking in this many times, or this many at a time. Now, the formula is going to be n factorial, which factorial means I just multiply all the numbers below it. So 3 factorial will be 3 times 2 times 1. And then over n minus r factorial. So let's take a look at how that works with the problem we just did. You'll see it's the exact same problem. How many 3-digit numbers can be made from the numbers 1, 2, 3, 4, and 5 without repetition? Now, that means I've got 5 objects, and I've got to take them 3 at a time. And I'm going to do a 5 factorial over 5 minus 3 factorial, which 5 factorial is 5 times 4 times 3 times 2 times 1. And then 5 minus 3 is 2 factorial, which is 2 times 1. And you'll notice if I do that, what's going to happen is these 2 and the 1 are both going to cancel out. And it's going to leave me with 5 times 4 times 3, which is going to be the same answer that I got before. 5 times 4 times 3. So what I'm saying is that this counting principle and the permutation, they work a lot the same way. And sometimes you can use the counting principle to solve a permutation question, and sometimes it's faster to use the permutations. So, if you get stuck, you can kind of take a look at both of them. Anyway, let's try this problem. If I've got how many 3-digit odd numbers can be made from the 5 numbers? All right, now again, we'll start with repetition. So again, I've got odd numbers. And when they give you a condition, well, what you got to do is start with it. So in this case, the numbers are odd. And what that means is that the last digit is odd. So what am I going to do? Well, I have 3 digits. And the first digit, the second digit, the third digit. But the condition is talking about the third digit. And it has to be odd. So how many odd numbers do I have out of my 5? Well, there's 3 of them. So how many numbers could take this spot? There's 3. Now, how many numbers, with repetition, could fill the first and the second slot? Pause this and go ahead and put those down. Okay, so hopefully you did that, and hopefully you decided that in this first spot I would have 5 numbers that go there, and because I'm allowed to repeat them, and then hopefully you decided that I've got 5 numbers that can go there, and then 5 times 5 times 3 is going to be 75, which means I've got 75 different numbers or arrangements. So, what about without repetition? Pause this and see if you can figure out what we would do with finding the number of odd numbers. Alright, so once again, without repetition, I still start with this third digit, and there's still 3 possible places, or three possible numbers that go there. And then I go back to the beginning, and then I ask myself, how many numbers could go here? Well, I already used a number. I don't know what it was. It was 1, 3, or 5, but it doesn't really matter. There's still 4 left, and that could go here. And then I look at the second digit, and I say, okay, I've used 2 different numbers. So what's left here? Well, out of the 5, there's going to be 3 numbers left. That's going to give me 4 times 3 times 3, or 36 different numbers or arrangements. So, let's try this. How many 3-digit numbers greater than 200 can be made from the 5 numbers? And again, we'll start with repetition. So, in this case, I've got a condition that says that the numbers have to be greater than 200. So, what does that mean the first digit should be? Pause it and tell me. Alright, so this first digit could be a 3, and it could be a 4 or a 5, but it also could be a 2. Hopefully you named all of those for the first digit. So in this first slot, how many different numbers could fill it? Well, there's 4 of them that could go there. And now if I'm allowed to repeat numbers, how many different numbers could go in the second digit? Well, there could be 5 that could go there. And then in the third spot, how many numbers could go there? 5 again. So how many different numbers could be created by the first, second, and third digit with these number of ways? 100 different numbers can be made, or 100 different arrangements. So now let's try it without repetition. Pause this and see if you can fill these in. Again, so I hope you did that in the first spot. Hopefully you decided that there are still going to be 4 numbers that can go there. But now that I've used up a number in the second slot, I only have 4 left. And then I only have 3 left for the last slot. And if I multiply 16 times 3, I get 48 different numbers without repetition. Alright, so what about this? How many 5-digit numbers can be made from these 5 numbers? So we'll start with repetition. And that means I now have 5 different spots. So pause this and tell me what you think can go in these different digits. Okay, hopefully you did that, and what you found, I'm hoping, is that in this first spot I could put 5 numbers, and then in the second spot I could put 5 numbers, and the third 5 numbers, and then the fourth 5 numbers, and the fifth numbers. I'm allowed to repeat all these numbers. So what's 5 to the 5th power? It's going to be 3,125 different numbers, or, again, arrangements, with repetition. So let's try it without repetition. Pause it and tell me or write down what it is you think the different possibilities for these digits are now. Okay, good. Hopefully you did that, and hopefully you decided that we've got 5 different numbers that can go here, and 4 different numbers that can go here, and 3 different numbers that can go here, and 2 different numbers that can go here, and 1 different number can go here, because I'm not allowed to repeat any of them. And you'll remember that 5 times 4 times 3 times 2 times 1, that's going to be 120. But more importantly, it's going to be the same thing as 5 factorial. 5 factorial equals 120. So if I've got to arrange a number of objects, and I'm going to arrange all of them, it's going to be that number factorial. All right, so let's take a look at the counting principle. And again, we talked about this formula a minute ago, and let's see how this formula works with this. Now, I've got 5 numbers, 1, 2, 3, 4, 5, and I want to create a 5-digit number. So basically, I have 5 objects altogether, but I'm taking them 5 at a time. That's 5 permutation 5. Well, if I use the formula, that's going to be 5 factorial over 5 minus 5 factorial. 5 factorial, we said, was 5 times 4 times 3 times 2 times 1. And then 5 minus 5 is 0 factorial, and it's kind of hard to wrap your head around a little bit, but 0 factorial is always equal to 1. So that means that even if I use the permutation formula, it's still going to be 5 factorial, because this is going to be over 1. So if you're asked to arrange a number of objects and you're going to arrange all of them, well, the easiest way to do it is to go ahead and do the number factorial. So let's take a look at this. How many different ways can 6 people be seated in 6 seats? All right. So in this situation, we've got 6 different seats. And basically what we're thinking about is how they can be arranged. And it's really similar to the number problem. But the difference is that if I've got 6 people sitting in seats, well, it's impossible to have any repetition because a person can only sit in 1 seat at a time. So it's no way one person can occupy more than 1 seat. So sometimes what will happen is they'll give you a problem like this and they won't mention repetition or not repetition because you're supposed to know there's no way that one person can be in more than 1 seat. Anyway, essentially I've got 6 different spots, and I got to figure out the number of ways to fill each one of them. Well, how many different ways can I fill the first chair? Well, there's 6 of them. How many different ways can I do the rest of them? Pause it and go ahead and fill those in. Okay, so hopefully you did that, and hopefully you found out for the second seat I've got 5 different ways, and then 4, and then 3, and then 2, and then 1. 6 factorial, because once again you'll notice that I'm just arranging 6 objects, 6 at a time. That's going to be 6 factorial, which is going to be 720 different ways that they can be sat. So keep in mind, if you're arranging n distinct things without repetition, it's just going to be n factorial. Alright, so let's again take a look at the formula. If I take the exact same problem, and I have 6 people seated in 6 seats, well that's 6 things, and I'm grouping them, or I'm taking them 6 at a time, and so that's just going to be 6 factorial over 0 factorial, and so that, again, it's just the same thing. So even if I use the counting principle, or if I use the permutation formula, I get the same result. So let's try this. How many different ways can 6 people be seated in 3 seats? All right, so now I got more people than I got seats. Now, you could think of the people as numbers, but again, people can't be repeated. So that's kind of the benefit of using the people. But again, if you want to think of them as numbers, that's fine. Just remember, we're going to be doing no repetition. So how many different ways can I fill the first seat, then the second seat, and the third seat? Pause it and go ahead and fill those in. Okay, so hopefully what you decided was the first seat, I had 6 different ways to fill that. And hopefully you decided that if the second seat, I had 5 different ways to fill that, and then 4 different ways to fill that. So it's going to be 6 times 5 times 4, which is going to be 100 different ways, or 100 different arrangements without repetition. So it's not 6 factorial because we're not using all of the different objects. Now again, if I take this same question and then use the formula, I've got 6 people and I'm putting them in 3 seats. Well, basically that means I've got 6 objects and I'm taking them 3 at a time. Well, what that is 6 factorial over 6 minus 3 factorial, which is going to be 6 factorial over 3 factorial. And you'll notice the 3 times 2 times 1, it gets canceled out, leaving me with 6 times 5 times 4, which is exactly what we just figured out a minute ago using the counting principle. So it's again another situation where I could use the permutation formula or the counting principle, and I'm going to get the same answer. Now what about this? We got letters now. I got the word rock. How many different arrangements can be made from the letters rock? These are called anagrams, where we just kind of move the letters around. And again, if I'm just moving letters around, then it can't be any repetition. So let's talk about that. What do you think I can do with that? I've got first letter, second letter, third letter, and fourth letter. Pause it, and then take a look and tell me what you think can go in each one of those spots. Okay, so obviously if I've got 4 letters in the first spot, I could put 4 different letters, and then in the second spot I could put 3 different letters, and then 2 different letters, and then 1 different letter. So even in this case, I've got 4 unique things, and I'm arranging all of them. It's going to just be 4 factorial. In this case, it'll be 24. So again, if we're arranging n distinct things, it's just going to be n factorial, whether it's letters, people, things. That's the way it's going to go. Now, again, if I look at the formula, the same exact problem, we're using the formula, it's going to be 4 factorial over 0 factorial, which again is 4 times 3 times 2 times 1. So what about this one? How many different ways can we arrange the word rook? R-O-O-K. Okay, so let's try that. I got 4 different spots for letters. What do you think you can put those in? Pause it and put those down. Okay, so hopefully you did that and you found that I have 4 different spots, and then 3, and then 2, and then 1. And then you get 4 factorial over 24. The thing is, though, there's a problem. And I want you to take a look at it. In this case, if I were to give these letters O's, the 2 O's sub-number, so O1 and O2. All right, so let's take a look at this. Right now I've got the word rook. And then I rearrange just the O's. So now the O's have been switched. But you'll notice the word is exactly the same word. I've changed the letters, but the word is still the same. The reason is I've got an identical object in my objects. So another way I could do this is I could rearrange the R and the K. And again, if I have the O, the first O and the second O, but then if I switch them, again, I've arranged letters, but the word is still the same. So the problem is, because I've got some identical objects, in this case identical letters, when I rearrange them, sometimes when I rearrange the identical ones, it doesn't change the word. So what I've got to do is I've got to divide out that. So basically the way this works is that I'm going to take the number of ways. If you've got a situation where you're finding the number of ways something can be arranged, and some of them are identical, you do the number of ways factorial, and then you divide it by the number of identical items factorial. So in this case, the O's are identical, so it would be 4 factorial over 2 factorial, or 12 different ways. Okay, so I'm going to end this video here. go ahead and check out part 2 for some more examples on this permutations and counting principle. Thanks for watching.